All right, so here's exactly what our code is going to do to talk to the color sensor. So I know the slave address of the color sensor is 41, so we're going to be using that number to communicate with the device and let it be notified that we're actually talking with it. All right, so the first part is actually we're going to test to see if we're actually connecting to the color sensor, and the color sensor is actually picking up whatever we send to it. So the first thing we're going to do is we're going to read the ID register of the color sensor. The address code for that is 146, and then once we read it out, we're going to go ahead and double check if it reads the correct number. So the value that should be coming out is 68. And then once we all have that all sorted out, we're going to go ahead and continue on and write the rest of our code up. So the first part is we're going to initialize the color sensor. So again, there are a lot of settings on this color sensor. So what we want to do is we want to adjust the sensitivity on it, and then we want to actually turn on the color sensor and let it start reading in data. So first off, we're going to go ahead and write to the RGBC timing register. The address code is 129, and we're going to set that register to 0. So what that does, it's going to set it to the maximum sensitivity of the color sensor. Then we're going to write to the control register of the color sensor. The address code is 143, and we're going to write that to 0. So what that's going to do is it's going to set the gain to 1. Then we're going to go ahead and write to the enable register, which has an address code of 128 to 3. And what this ultimately does is it turns on the analog to digital converter on this chip. So it's actually going to start collecting data, and we're going to turn the device on so it actually will start running. Okay, so once we have everything initialized, this means that we can actually now start collecting data from it. So we're going to go ahead and read data from the color sensor. So first off, we're going to go ahead and read 2 bytes from the clear data registers. The address code is 148, so we're going to get a 16-bit value of the actual ambient light conditions. Then we're going to go ahead and read 2 bytes of the red data. The address code is 150, and so we're going to get a 16-bit value that represents the red data, or the red color that it picks up. And then we're going to do that with green, and we're going to do that with blue. And then once we have that, we're going to go ahead and figure out from there on out exactly what we're going to do with these numbers. First off, we're going to go ahead and just output this to the screen, and then we're going to write up a processing sketch that will actually output the actual color that it picked up. All right, so we're going to go ahead and get started with writing up this code. So I copy-pasted all the little steps that we need to write this code up, and I commented it just so that you can follow along with exactly what I'm doing. All right, so the first off, we actually want to instantiate an I2C class. So this is actually going to create an I2C line. So I'm going to go ahead and call it I2C, and as the API describes, the first pin you want to put in is the one that has the data line, and then the other one is the one that has the clock line. So for our case, it's going to be PTB1 is going to be the one that has the data line, and then we're going to have PTB0 be the one that has the clock line. Okay, once we have that done, we're going to go ahead and we know that the slave address of the color sensor is 41, so we're going to go ahead and store that into a variable just to make it so that it's a lot easier to write this code up and makes a lot more sense. So I'm going to say int color sensor address is equal to 41. Okay, now there's one perk about this that you need to keep in mind when getting an address from the specification sheet. So if we go ahead and go to the API for this, you'll see that for the case of the read or the case of the write, it'll say that the bottom bit of the address is forced to 0 or 1 to indicate a write. So as you can see on the calculator over here, we have 41 as the decimal value, and you can see the bits right here. So this is kind of a problem. So if you want to write something, what's going to happen is that it's going to force this little bit right here to be 0, and that's not the right slave address. So what you actually want to do is you want to go ahead and bit shift this up by 1. So we're going to go ahead and move all the bits and move them all by 1. So you can go ahead and just look over here on the side, on the top right. If I bit shift it by 1, it'll move these bits up like that. And that'll make it so that this last bit right here can be set to 0 or 1 to indicate a read or a write. So actually what we're going to do with this code is go ahead and do that bit shift operation as we store that data value into the color sensor address. So we're going to go ahead and say shift up by 1. So that's exactly what this sign means, and again, this means bit shift up by 1. All right, so we have the slave address all set up. Now we're going ahead and test to see if we're connected with the color sensor. So I'm going to go ahead and write int main here. Actually, it should be int main in here, because we're going to go ahead and write the code up underneath the comments as we go. So I'm going to go ahead and just put this right here, so I have some space to work with it. All right, so we're going to go ahead and test it with connecting with the color sensor. We're going to first read from the ID register, which has an address code 146, and the output should be 68. So let's go ahead and get started here. So we're going to go ahead, before we do this, we're going to go ahead and set the frequency, the clock frequency to 200 kilohertz, just for the sake of it. The maximum clock frequency in our case is 400 kilohertz. But when I set it to 200 kilohertz, just to ensure that at least the data is going to be transferred across, and it's a frequency that we're happy with. Okay. Now, anyway, back to this. So what we're going to do is we're going to go ahead and follow the command code, exactly how to read things. So we can actually see right here the I2C read protocol is we're going to first send a slave address, set a write, and then set a command code, and do a repeated start condition. So this first chunk right here utilizes the I2C.write command. So we're going to go ahead and use that command. So we're going to go ahead and type in I2C.write. And the first input argument is the address itself. So I'm going to go ahead and put the address here. And then we're going to go ahead and input whatever is the next character byte, or whatever is the next thing. So it should be the ID register value. So a thing to keep in mind is that this API takes in character arrays. So you want to go ahead and make a character array to store this data value. So a character array pretty much is just a giant row of character values, and you can go ahead and identify this. So this is one that's going to store only one data value, and this data value is going to be 146, which is our ID register. In fact, I should not call this data. I should call this the ID register value. Okay, so we now have that, and we're going to go ahead and type in ID register value over here, because that's the next byte that we're going to transfer through. And then we have to identify exactly how many bytes we're going to be transferring. So I'll transfer only one byte after the slave address, and that byte in particular is the ID register value. And then again with the command, it says we want to have a repeated start condition. So to define whether or not you want to have a repeated start condition, you either say true or false. So true means we're going to go ahead and create a repeated start condition. All right. So once we have that, then we're going to need to create a character array that's going to store the data value of the register. So we're going to say character data, which is going to store 1 byte because that's the register value, because the register value is going to be 8 bits. And we're just going to go ahead and identify this as just 0, just instantiate as 0. All right, so then we're going to use the I2C.write command, or .read command, sorry. And again, the first input argument is the sensor address. And then you want to actually input what is the character array that's going to store this data. So we're going to say put data in there. We're going to read 1 byte, and then we're going to go ahead and say false because we don't want to have a repeated start condition. We just terminated the operation, and we've stopped I2C communications. All right, so data should now have the ID register value, so it should be 68. So we're going to go ahead and test to see if we actually got that. So we're going to go create an if statement, and we're going to say if data, which is 0. Data 0 just pretty much means that I'm going to read the first data in the character array, which means in this case, since there's only one data value, we're just going to read whatever was outputted when we read this. So data is equal to 68, and then we're going to go ahead and do something to identify whether or not we actually got it or not. So we can do a variety of things. We can make it so that it prints to display if it read successfully or not. But the fastest way to do this, in my case, is just to make it so that we'll turn an LED on and off. So on the KL25Z, there is a multicolor LED on it, and you can access it using a digital out. So I'm going to say digital out, green, and we're going to go ahead and define the pin for this. So the pin for it is called LED_green. And then at the very beginning right here, we're going to go ahead and instantiate it so that the green is actually off. So there's a funny thing about this where the LEDs, when they're 1, it's off, and 0, it's on. It's a small little trick, but that's just exactly how they hardwired it up, unfortunately. So in the if statement right here, what we're going to do is actually we're going to turn on the LED, and then we're going to turn it off after 2 seconds. Okay. Else, if this isn't true, what's going to happen is we're just going to go ahead and just have a green equal 1, which means the LED is off. So if everything works fine and we actually read it correctly, what's going to happen is that the green LED is going to turn on for 2 seconds and then turn off. So we're going to go ahead and compile this code and then throw it into the microcontroller and see if everything just works. Okay, so I have it all hooked up and wired up. I turned off the LED because it's too bright and it actually makes it so it's a bit harder to see this, but I'm going to go ahead and upload the code onto the microcontroller. And then I'm going to go ahead and reset, and if it turns green, turns the LED on for 2 seconds, then the code's going to work. And that means that we actually read the ID register value correctly. So I'm going to hit reset. As you know the green LED actually turned on for 2 seconds, turned off, so we're good. So we actually are able to communicate with this chip.